Hello, my name is Ozan, and I'm a senior researcher in Microsoft Research Cambridge. Today, together with my colleague Anton, we are presenting our latest research work in Project InnerEye. In particular, we will talk about how we augment radiotherapy workflows with deep learning models to save clinicians time and empower them. The talk will be structured in two parts. In the first part, I will briefly describe the conventional radiotherapy workflow and how we augment it with our machine learning models, followed by our research findings. And in the second part of the talk, Anton will introduce the InnerEye open source toolkit and explain how to build the state-of-the-art deep learning solutions using in-house datasets. Before I begin explaining these models, I would like to give you a brief introduction of the role of medical imaging. As you might know, the future of medicine lies in early diagnosis and individual tailored treatments, also known as personalized medicine. It aims to deliver the right treatment to the right patient at the right time. And medical imaging has always been personalized and is fundamental to almost all aspects of personalized medicine. When we look at the history of radiology, we have seen a significant progress over the decades from digitalization, management of scans in hospitals, to clinical decision support systems. And in the future, we will be able to collect measurements from scans in a more accurate manner and integrate this information with multiple sources to achieve definitive diagnosis and more focused treatment. And as Project InnerEye, our vision is to be part of this process by democratizing such image analysis systems to empower healthcare providers for better patient outcome. So let me give you an example of one of our projects. Radiotherapy is one of the research areas where we have been focusing on over the last few years. In cancer treatment, as you might know, there are several ways of treating patients, ranging from surgery, chemotherapy, to immunotherapy. And intensely modulated radiation therapy is one of them. It has become a key component of contemporary cancer treatment. A linear accelerator, also known as LINAC, is a device commonly used to deliver the radiation treatments, as you can see on the left-hand side. It focuses high-intensity radiation to destroy tumors while avoiding surrounding healthy organs, and this requires an execution plan in order to maximize the radiation dose over cancer cells and minimize it on healthy tissues. For this reason, it is essential to produce personalized radiation treatment plans that match patients' unique anatomical configuration. And if we look at the standard clinical workflow for radiotherapy workflows, we see that a couple of steps. And in the first step, patients first of all undergo tomographic scans. And later, radiation oncologists manually annotate these scans to identify target tumors and the surrounding healthy organs, which are later used to create a dose plan to guide the treatment. And the treatment is delivered in multiple fractions with lower dose amount, but the same plan is used over time. And the planning procedure requires manual delineation of tumor tissues and the surrounding target organs in these 3D volumetric images. As you might expect, this can take up anywhere from 30 minutes to hours, as there are often tons of Excel slices and a few target organs to be annotated. In addition to that, there is a clear demand in standardizing the quality of this procedure across hospitals, in particular in clinical trials. And here on the left-hand side, you're seeing 3D delineations generated on prostate and head and neck CT scans. So in our research, we explored how machine learning could fit in this process and augment it in a clinically useful way. This way of approach towards healthcare-related problems differentiates us from other machine learning labs. In our approach, we aim to automate the contouring process I just mentioned in order to save clinicians time, whilst keeping them in the loop in case manual intervention is required. In more detail, our deep learning models provide an accurate initial set of contours that the clinician must review, and most of the time, they do not need any adjustments or very minor ones. And additionally, this can allow more adaptive forms of radiotherapy, where plans are updated across visits or fractions, thanks to the reduced time demand. In the next slides, I would like to walk you through our methodology and our validation strategies. on showing how effective these models are and how they can actually reduce the planning time. First of all, I would like to mention that we have recently published our research work in a clinical journal, JAMA Network Open. In this research, we basically try to evaluate the clinical utility of deep learning models in two particular radiotherapy domains, namely head and neck and prostate cancers. And this research work mainly tried to find an answer to the following question. Can machine learning models achieve clinically acceptable accuracy in image segmentation tasks in radiotherapy planning and reduce the overall contouring time? As you can see, we are not just interested in model accuracy obtained on a holdout test set, but we are interested in how could these models actually help radiation oncologists in their daily routine. And this obviously requires clinically acceptable accuracy and incorporation of these models into frameworks in a minimally disruptive way while ensuring clinical safety. Besides this research question, we have also focused on other aspects. In particular, how well these models generalize on external datasets and different cancer types, and how these models could be actually integrated in clinical workflows, and what will be the interactions required. These are the aspects in addition to the reduction in annotation time. And to give further information about this, we followed the CONSORT AI guidelines, which were recently published and dedicated to randomized clinical trials. Our work is more classified as process improvement, but we believe that some of these guidelines can be useful for studies that involve machine learning or AI in their workflow. So to begin with, I would like to present our proposed clinical workflow in a research setting. The boxes shown on the the white boxes shown on the left-hand side illustrate the conventional workflow. And on the right-hand side, we're illustrating the model training and inference performed in Azure Cloud. The presented workflow enables oncologists to use their existing clinical systems for review and editing the contours, as you can see, once the images are processed and the contours are available, which makes this technology more accessible across clinics as the existing workflows are maintained, and in return, the required contours will be available for planning in the order of minutes rather than hours. And lastly, it is important to note that this is not a clinical product, but a research study in machine learning and healthcare domains to check the feasibility and potential benefits of AI in radiotherapy planning. And the data sets that we use in this study are also very important. And I would like to briefly explain what kind of data we have used in this study. As you might know, one of the barriers to the uptake of machine learning in clinical use across different hospitals is that most of these models are only trained on a data set from a single institution or focus on a single task. To overcome this problem, we use anonymized data sets from 8 different clinical centers across the globe. All identifying information was removed from the data by the clinical sites prior to the transfer to Microsoft Research. And training and validation on multi-site is an important aspect, as the lack of generalization can reduce the potential utility of machine learning in real-world applications, such as due to different image acquisition settings or patient cohort groups. To give further details on the datasets, the proposed models were trained on an anonymized set of 519 pelvis and 242 head and neck 3D CT scans. And more importantly, these images were categorized into 2 different buckets per radiotherapy domain, as main sites and the external sites. The images put in the external sites were not used at training and validation of the models to be able to test the model's generalization ability on previously unseen datasets. In a way, we have performed a blind evaluation. And these scans were manually contoured by an expert reader and 3 senior radiation oncologists. And in particular, we were interested in 15 different structures, and we were trying to produce segmentations for those structures. So let me walk you through what kind of methodology we have used to generate these auto-contours. The image segmentation model is a state-of-the-art convolutional neural network, as you can see, with millions of learned parameters at training time. And the design is similar to a 3D unit architecture, with some modifications to better utilize the computation hardware and increase the number of samples used in model parameter updates in stochastic gradient design. This includes mixed precision representations, memory-efficient tensor aggregation blocks, and model partitioning across multiple hardware. And we use Microsoft Azure Machine Learning to develop and train these models across 20 NVIDIA Tesla cards. I would like to get into more details on how we actually partition these models, because this technique allows us to process full 3D volume scans, and it eliminates the need for image patch-based processing of scans, which is a commonly used approach, but it can lead to redundant computations and inferior performance at test time. By using this model partitioning, large contextual information and batch statistics are collected for each parameter update. And contextual information usually matters in medical imaging domain, where tissue contrast is low and prior knowledge is required, such as in head and neck scans. And how did we perform this task? To begin with, we first looked at the memory fingerprint of each layer. And after identifying the memory need of each layer, we tried to distribute these layers across multiple hardware in a balanced manner while ensuring the continuity of operations within the computation graph. Now I would like to show you how these models perform in a qualitative sense before we discuss about the metrics and the quantitative measurements. So here we are seeing the results obtained on 3 different subjects coming from main and external data sets. And the auto segmentations were generated for 6 different structures on these pelvic CT scans. And what we commonly see is that on the external data sets, the scans might sometimes have larger true plane resolution, and this can actually be a challenging situation for the models. But more importantly, when we look at the head and neck scans, on the external data sets, we have actually worked with data images containing imaging artifacts and lower tissue contrast. And this was mainly associated with beam hardening and metal artifacts. And training models on a diverse set of data sets, as performed in this study, is an effective way to cope with these kind of challenges. And it is also important to note that the annotation protocol differences across sites is an important aspect. And we had to review the data sets and their labels to ensure the consistency between them. So in the remaining slides, I would like to present you the quantitative metrics that we used to validate these models and how the models perform. So to begin with, we should talk about the metrics that we use just to understand how, in terms of the accuracy, how well these models perform. And then later on, I will talk about the clinical utility aspects. And here we are seeing 2 commonly used metrics in the literature. Here on the left-hand side, we are seeing the volumetric agreement measurements obtained with DICE score. And on the right-hand side, we are seeing the surface-to-surface distance metrics commonly used to understand how gross the mistakes produced by the models are. Volumetric measurements usually range between 0 to 100% agreement, where 100% agreement corresponds that 2 volumetric contours basically have a full agreement. But I would like to note that these metrics do not necessarily directly translate into time savings. However, it's a minimal requirement for clinical acceptability and measuring inter-observer variability. And additionally, there's a minimal requirement bar that we need to meet so that clinicians actually consider using these auto-segmentations as a starting point instead of doing it from scratch. Here in this box plot, we are seeing the results obtained using this DICE metric on 6 different structures on pelvis scans. And these DICE scores, were computed on test images coming from both external and internal datasets. And the reason why we performed this experiment was that we wanted to see if the model performance drops because of the generalization issues. And ideally, we would like the model to perform consistently well on both internal and external sites. And to analyze these results further, we performed statistical testing to check if there is any statistical difference between these sets of images or the performances. And what we observed is that basically our models consistently perform well on both external and internal data sets. It's also important to note that these models can always be fine-tuned on on-premises data sets if it's required. For example, data shifts could be severe due to acquisition protocols, and fine-tuning can always be used as a backup option. And more importantly, I think we should also look at the clinical utility aspect, namely time savings. And this experiment is a more human-centric approach to evaluate the performance of a machine learning model. And this is one of the main differentiating points of our research work. Here we're showing the potential time savings, and this could actually translate into clinicians having more time to spend with their patients for person-to-person interactions. Let me explain you in more detail what we did in here. The blue bar represents the time taken to perform image segmentation task manually by an expert radiation oncologist on 10 head and neck CT scans with varying imaging quality. And the bottom bar shows the model's runtime plus the time for the same expert to review and update the contours while ensuring the clinical accuracy. And we observed similar gains on the prostate scans, and time taken was less due to fewer number of structures to be annotated. And in these experiments, an in-house image annotation software was used both for contouring and correction tasks, which includes assistive contouring and interactive contour refinement tools. And we expect that these gains can be further extended as we start including more target structures in the planning stage. Reduced planning time is an important utility of these models, as you can see. However, this should be complemented by clinically acceptable contours generated by these models as well. And in order to assess this, we ran a separate experiment together with multiple clinical experts and measured the inter-expert variability in this contouring task on a subset of images. So let me begin with how we collected the annotations. A subset of images from both radiotherapy domains were annotated by a set of experts, as you can see on the left-hand side, multiple times. And the gold standard contours were extracted by aggregating their candidate annotations. And afterwards, we assessed the variability observed across these experts to understand the bounds of clinical acceptability and perform the statistical agreement analysis between the contours generated by these experts and the models. So let's have a look at how do they look like in a qualitative manner. Here we're showing the prostate contours collected from the model and the experts obtained on two different pelvis scans. The color map shows the surface distance errors with respect to the gold standard contours I just mentioned. And the red color represents the surface points with distance error larger than 2.8 millimeter. So the main thing that we should focus on here are these contour errors. And these contour errors are mainly concentrated at the surface points adjacent to the bladder and the rectum, mainly at the interface of the organs. And the model contours are aligned with the ones originating from the first expert. So our model basically does not perform arbitrary segmentations, and their errors are correlated with the expert's errors. And if you look at the results from a quantitative perspective, what we did is we looked at the DICE scores and the variability across experts and how the model performance fits within that distribution. And we see that there's statistical agreement between these two sets of measurements. And for this, we performed Fleiss-Kappa analysis and generated blunt-Altman plots. For further details, please check the supplementary material of our research paper. And when we look at the results obtained on the head and neck scans, we also saw statistical agreement between the experts and the model, except for submandibular glands. And the reason why we observed this difference is mainly associated with low tissue contrast and the absence of the organ due to previous resection surgery. In short, out of 15 structures, we have observed clinically acceptable performance on 13 of these structures that we have used in the study. And lastly, I would like to give you a short summary of part of the statistical agreement analysis we did. And here we're seeing the blunt-Altman plots obtained for two different structures, namely prostate and rectum. And the purpose of these plots basically is to understand how well the model performance agrees with experts. And we would like to analyze this on a sample basis. And here each point is representing the image or the patient data that we have used in this study. And if the models and the expert performance agrees, we will ideally expect these to fall between the confidence intervals. And this is what we have observed for the structures that we used. Additionally, we have recently released a blog post describing the findings of our research paper and also the open source toolkit that we have recently released. So if you would like to check out this blog post, please follow this web link at the bottom. Next, my colleague Anton will introduce the InnerEye Deep Learning Toolkit. It is an open source library, and he will talk about how to build the state-of-the-art medical image segmentation models in Azure in a scalable and efficient manner using in-house imaging datasets. I would like to thank you for your attention, so let me transfer to Anton.
Thanks very much, Ozan. My name is Anton. I'm a principal software engineer in the InnerEye team. So Ozan has just presented a set of really amazing research results. But I think what matters most here is that these are research results that not only look great on paper, but they have been validated in a clinical context. So we know that using such AI models in a clinical workflow can really make a tremendous difference to what is otherwise a really mundane, time-consuming, tedious task for clinicians. Now, these days, researchers are not only asked about the great results that they produced, but they are also asked, how did you achieve them? Is what you're telling us really reproducible? And these questions are asked in particular also to research results that come out of big tech organizations. So we've tackled these questions head on by just putting all of the code that we have been using in this research project out on GitHub. So that includes all of the model architectures, all of the tweaks, all of the boring bits, if you will. Now, there was probably a second, now even bigger goal that we wanted to achieve with open sourcing our code. Now, building these clinical grade segmentation models really requires a lot of expertise at different levels, at an infrastructure level, at a machine learning level. And we wanted to make this process a lot easier for organizations in particular where technology is not the main focus. We're thinking in particular of hospitals here. So hospitals usually have tons of data. They have burning problems where maybe a well-built AI model could make a tremendous difference, but they do not have the time or the expertise to really invest in getting started on machine learning model building from scratch. And by open sourcing our toolbox, we wanted to enable those organizations to do as well as we did. Now, one important feature of our InnerEye toolbox is really that it tries to make best use of cloud computing. And I feel that cloud computing is really a big enabler here, in particular for organizations where technology is not the main focus, because it just dramatically lowers the entry barrier to doing deep learning at a reasonable scale. So what the cloud enables us and other organizations as well is that there is no longer a need for making a humongous upfront investment in an expensive GPU cluster. We can get everything out of the cloud and in particular set it out in such a way that it scales precisely to the workload that we have today. And most importantly, this also means if we're not building AI models today, we're not going to pay for it. But apart from the infrastructure level, using cloud computing for building AI models also makes a tremendous difference to how a team can operate. And we've certainly experienced that in the InnerEye team. So our previous workflow was pretty much that everybody was working on their individual GPU machines, and all of our model building results were sitting on these individual machines, effectively siloed from the rest of the team. Now, when we're switching everything to cloud first, it means that all of our modeling results are stored inside of an Azure machine learning workspace. And now this gives us a completely new level of transparency. I can now just take any of my colleagues' results, dig in, compare with what I have achieved. And so we are really able to push forward as a team in a completely new fashion. It also gives us a lot of traceability and reproducibility if, for example, at some later point, we wish to implement something like a quality management system. And the cloud is also great when it now comes to putting these models just out of their pure training context. And if we wanted to, for example, spin up a small web service and use these models outside in a real-world workflow, for example. Now, let's talk a little bit more about what the InnerEye toolbox brings on top of these general cloud computing benefits. The InnerEye toolbox contains all of the model architectures that we've used in order to achieve the results that Ozan has just presented and that have been published in our JAMA paper. There's a ton of reporting and diagnostics built in. You have capabilities like model comparison, so that we would know, for example, if we build a new prostate segmentation model, how does that stack up against the best prostate segmentation model that our team has built so far? So all in all, it means that you would have to write a lot less of mundane, boring boilerplate code. But while everything comes with a cloud focus, we absolutely recognize that it is important for model diagnostic and development purposes to be able to also run on individual GPU boxes. So this is why we focused on building a seamless transition. So you can start out on your local box with your model development and switch to using the cloud with just one single additional command line argument. I wanted to briefly mention also the technology stack that we are using here. So on the infrastructure level, we are using Azure Machine Learning. For the machine learning bits, this is all based on PyTorch and PyTorch Lightning, the latter for doing all of the distributed training, for example. And on top of that sits the InnerEye Deep Learning Toolkit. And with this toolbox, you can now build segmentation models, classification and regression models, and also sequence models. And most of those models can be built with a combination of non-image and image features. Let's also talk for a moment about the machine learning lifecycle, because I'm going to present some steps of that and how they relate to the InnerEye toolbox in a minute. So we would start out here with data in DICOM or NIfTY format. So DICOM, of course, being the predominant format for medical images. With data suitably prepared, you would now, in the InnerEye toolbox, you would write a model configuration. That's a piece of Python code. You would run that through the InnerEye trainer. You would get a performance report. You would inspect that, and based on the performance that your model currently achieves, you would now tweak the model configuration, change, for example, the capacity of your model, change crop sizes, something like that. However, it is also important that, in particular in the medical domain, we should not treat the data as a given. So the performance report really also highlights cases that hint at the data being in somewhat inconsistent or incorrect. So when you analyze the performance report, it may actually mean that you have to go back to the data in the raw DICOM format and, for example, ask an expert to review specific segmentations and correct them. Once you're done with your model building, then you would have the option to deploy it in some form of validation environment. And eventually, you would also want to monitor any model that is deployed in production. So this is all very general and applies to all machine learning models. Now, how do these steps look like specifically for the InnerEye toolbox? So we would start out with data. So data for model training is organized here by folders. So you would have a folder for each patient. So here in this example, this is patient 0, patient 1, patient 2. This is an example from a public lung segmentation challenge dataset that we're also using in the model documentation. For in each folder, you would have a CT scan for the patient, and you would have binary masks. So these binary masks have the same size as the CT scan, and each pixel here in this binary mask means is the corresponding pixel in your CT scan, is that part of the heart, yes or no? Is that part of the left lung, yes or no? And we would have that for all of our patients. You would then take this file structure and cook it into a very simple dataset.csv format. And here in the last column, we have what we call channels. And we're going to refer to these file paths or channels when we now build the model configurations in the next step. So this is an example of how a model configuration for this lung segmentation challenge would look like. You would write a piece of Python code, a new class called lung that derives from the base class for segmentation models. And there are essentially only 3 things that you need to specify. You would have to specify a channel name that points to the files that contain your input CT scan, and you would have to specify the 5 anatomical structures that we want to segment. The last piece of information is pretty much a folder name. Where in Azure does this dataset actually live, or where on your local box does it live? The rest is something that's already in the fine-tuning range. So many of these settings are already pre-populated in the base class. So if you want to tweak, for example, the number of feature channels in your unit, this is how you would specify that. You just pass an additional argument here into the class constructor. Now, with these things in place, the dataset and the model configuration, you're already set for running the InnerEye training code. So you would create a Python environment and activate it, and then start the InnerEye runner and specify the name of the model that you want to train as a command line argument. And then it would go ahead and start training on your local box. If you have a GPU on your local box, it would use that, otherwise the CPU. Now, if we wanted to do exactly the same thing running in the cloud in Azure Machine Learning, then you would just specify an additional switch --AzureML equals true. And what that does now is effectively take a snapshot of the code that lives on your local folder, sends it over to the cloud, it allocates a virtual machine in your GPU cluster and starts the training there. So this whole process takes about 20 to 30 seconds, and then you're done. Once the job is queued in the cloud, you can now go over to the Azure Machine Learning workspace and inspect your current runs. This is how that looks like. So let's inspect the most recent run here. So we have all of the information there about which command line arguments did we actually give this training run. We have information which Git commit was used upon submission. There is a set of editable tags that you can use to attach additional metadata. And you can pretty much watch the training by just inspecting what the latest console out of your job was. There's graphing functionality built in. You can pick a couple of dice scores, for example, for different structures, and monitor how they evolve as training progresses. In the Snapshot tab, you get the complete record of the code that was used for this specific training run. So if you want to, for example, validate whether a specific tweak that you've played with is really switched on or present in the code for this run, this is how to do that. But now that we have all of our results in a nice table form in the cloud, we can also very simply create a dashboard. So this quick screen grab shows how to do that. we can now, for example, specify that we want to show the validation set loss in our table. We can also pick the validation set dice score for the left lung lobe. Let's add that to our columns as well. Off we go. And we have a very simple dashboard. We can do the same thing for graphs. If we want to see how, for example, training progresses and converges for the most recent set of runs that we've selected. Now let's pick again here the validation set dice score for the left lung lobe, and off we go. So we've tried to make best use of all of AzureML's built-in reporting capability, but there is also something very specific to segmentation models that we've added here. So in each training run of a segmentation model writes a HTML file that is effectively a Jupyter notebook, and this has all of the rather specialized reporting here. We would get an overview table of dice score for the different structures that our model is predicting. We'd get some key graphs, and we're repeating the whole thing for typical segmentation metrics, the dice score, the Hausdorff distance, and the mean surface distance. What is also contained in this report here is a set of structures, or rather a set of patients for which the model performs particularly poorly. So you can now go back and inspect, for example, the ground truth for some of the patients. It could also happen that you realize that your model has hit the capacity bounds of your GPU. So if you want to now start training on a larger GPU, this shows how easy it is to actually start up a completely new GPU cluster. You just pick the type of GPU that you want. Say, okay, I want my cluster to have at most 11 nodes, and off we go. And within less than a minute, we now have a new GPU cluster to run our training on. There are a couple of other capabilities that we should maybe add here. So you can turn on in the model configuration to also run cross-validation and hyperparameter tuning. Both of those would make best use of the cloud in terms of scheduling just parallel training runs. So doing 5-fold cross-validation no longer means that you have to wait 5 times longer, but everything is run in parallel. So it saves you just a ton of time. And you can also build ensemble models, similar to what we've done in the JAMA paper. And again, this is happening in parallel. Now, how does this all fit into a bigger picture? So if we want to evaluate some of these research models in a hospital setting, this is how such a clinical workflow could look like. So you could hook up the model with the hospital PACS system. You would send it over to a gateway system. So each pelvic CT scan, for example, could now, by the gateway, sent to a prostate segmentation model that is running here in the InnerEye inference service. And this model again comes out of the Azure machine learning training. And once the model has been finished, it would send back a segmentation that again goes back into the PACS system, and doctors can now inspect, correct, approve, and do something else with this model, with this segmentation. And we are at the moment working to put those additional pieces in place to make it easier for everyone to evaluate such kind of models in a typical hospital setup like I'm showing here. And this should work both in the cloud, but also on-premise. So if your compliance model, for example, requires that data does not leave the hospital trust boundaries, there should be a way for you to do that. So all of this work is, of course, only possible with the help of a lot of people. some of whom are listed up here. Everyone here has contributed to different aspects of this work on the machine learning side, on the technology side, on helping us better understand all of the clinical requirements. And I would also like to call out all of the great support that we got from the Azure machine learning team. If you would like to get in touch with us, please visit us on these web locations. And with that, I'm going to end. Thank you very much for your attention, and I'm looking forward to your questions.
Hi, everyone. Thank you for joining us today. My name is Ozan, and together with my colleague Anton, we will now have a live Q&A session. Over the next 15 minutes, we're going to be answering questions from the audience, in particular the ones related to the segmentation models and InnerEye Deep Learning Toolkit. If you have any questions that you would like to ask, you can use the Q&A window to submit them during this live session. Maybe we can get started. Anton, our first question is from the audience. Can you run inference on the CPU? Can you leverage Azure Stack to run inference on premises instead of in the cloud?
Thanks, Ozan. Given the size of these models, it is not really feasible to run inference on the CPU. However, we are working on a full integration with Azure Stack Hub, so that you can indeed run inference on-premise instead of the cloud. So this should enable, this should cater in particular for people who have a very stringent privacy model where data cannot leave, for example, the hospital boundaries. I hope that answers the question. Ozan, let me fire back with a question to you. We have here a question. In the future, are you planning to expand your studies to include other modalities such as X-rays and other diagnostics such as pneumonia?
Oh, thank you, Anton. This is a very interesting question. We have been considering expanding the toolbox for other modalities as well. And so within each modality, there are obviously application-specific challenges. In particular, if you talk about MRI modality for radiotherapy planning, for example, there will be challenges in terms of tissue contrast, image resolution, and we basically need to take these variations in the input space into account when we train our models and do the training. But the proposed underlying technology is generic and it's not application-specific. In that regard, we do not see any big challenges for expanding it to other modalities. We hope that this answers the question, and then maybe I can pick one from the list. Anton, there's an interesting question for you. It is great to hear about the reproducibility of the results. Can you summarize how do you ensure you're able to do that?
Thanks. Yeah, so this is handled at two levels. Firstly, we need to make sure that all sources of randomness in the code itself are carefully controlled for. So this means things like random seeds, obviously, but also multi-threading. The PyTorch backend also has some potential sources of non-determinism here. But I think the more important thing is to also treat data sets as immutable. So we need to really make sure that a data set has a unique ID, a unique structure, so that if we're running the same model on the same data set a year down the line, we must get the same results. So we have backend infrastructure to cater for this data set immutability. However, this is at present not part of the toolbox.
Great, thank you, Anton.
Ozan, should I just pick one for you here? There's a question about the time saving of anatomical segmentation, the impact on the total time to deliver to do a high quality dose plan for radiotherapy.
This is also interesting. So in our study, what we looked at is basically we looked at the time required for experts to make corrections on these auto-generated segmentations to ensure a similar quality those plans. So in that regard, when we did this time-saving analysis, we didn't try to compromise from the quality of the plans. And this experiment was conducted together with radiation oncologists. So the main purpose was basically, while ensuring the high quality, can we actually reduce the time? So in that regard, this was our core priority. And maybe I can pick another question from the list. Anton, this is an interesting one again, and related to the previous ones. How many GPUs are needed to infer the models? Generally, one does not want to use 20 GPUs as in training, not necessarily wants to use the GPU on the cloud for inference. Did you try to reduce the memory demands?
So the first part of the question, how many GPUs are needed for inference? We are using a single node with 4 rather spacious GPUs. And we were using partitioning the model across multiple GPUs so that we can really feed in like large crops and reduce all sorts of otherwise like stitching artifacts. We were trying to be as careful with memory demand as possible. However, in particular, patch size has a huge impact on model accuracy, and we really wanted to push the model accuracy to the maximum possible with our given hardware. So the models are, in the end, on the memory demanding side. Okay, I hope that answers the question. What's on a question for you here? Have you considered interaction loops instead of doing an initial segmentation with a single correction phase? Can you say something about that?
Yes, it's a very interesting point. So in our experiments, we haven't considered this. Obviously, such active segmentation approach will be definitely interesting to explore in the research setup. That basically requires a data set where we collect with experts and they understand their corrections for each possible segmentations that we produce, and that will involve more human and computer interaction. But yeah, we haven't explored this in this study. I can maybe ask one more question, Anton. From that list I'm going through, is it possible to see the code for 3D unit on your GitHub, or are they only available through the AzureML platform?
Yeah, all of the code that was used to produce this paper is on GitHub, and that includes also the model architecture with all of its details, so including model parallel, so the splitting of the model across multiple GPUs for inference. This is all rightly available in the GitHub repository. Okay, Ozan, let me pick another question for you here. There's one here. In your presentation, you highlighted training different parts of the 3D VNet on multiple GPUs. We've tried similar approaches. Could you comment on the trade-offs of such an approach? How would it compare with deeper 2D networks and making inferences per slice?
Very good question. So maybe we can talk about why we use multiple GPUs. First of all, what we have observed is that to achieve high quality auto-generated contours, we need to teach these models and make sure that they understand the anatomical context. And that will require, obviously, that we provide large input patches or volumetric patches to these models. And in return, the limitation is basically the GPU memory. So to address that challenge, we have been basically utilizing multiple GPUs, and that gave us a big advantage. So in that regard, if we try to use a deeper 2D network, we will probably run into the problem of limited context, that we need to understand the 3D view to be able to generate a good quality delineation. So this was the main reason why we opted for this design choice. And maybe I can pick one last question.
Let me just add a quick postscriptum to this question. We had another question in the same direction. Is this true 3D training, or is it training on 2D images? So from what you just said, yes, it is true 3D training.
That's correct. Thank you, Anton. Anton, I have a question from the list. What do you see as the potential extension of this framework for future wider adoption of this technology to be used in radiotherapy planning? What do you see as the challenges?
For wider adoption, we need to make sure that once the models are trained, we have easy ways of deploying them into a clinical environment, so where people can then further evaluate these models specifically for their for the types of scans that are taken in that specific hospital. So simplifying deployment and simplifying evaluation in a clinical context, and also making sure that the toolbox supports all of the things that are needed for example, quality management systems, for like whatever clinical approvals that such a model needs to go through in the specific hospital where people are looking into those. So
thank you.
So it's around, yes, deployment plus making sure that it can be quality approved and easily.
Thank you, Anton. Maybe I can add a few more details from machine learning perspective to this question. So we will need to consider the robustness of these models to different patient groups and variations that we observe in imaging data. In our research study and in the publication, we have done our best effort to test these aspects of these models across different population groups and hospital setups. But I think for future wider adoption, we need to make sure that these models are tested and produce robust outcomes, regardless of like the variations we see. So it will definitely require a further evaluation. We hope that this answers the question. Anton, do you have any more questions from the audience regarding the paper?
Yes, absolutely. There's one here. How do different devices affect the accuracy or precision of the machine learning model results?
Yes, this is a very interesting question, and it's also related to the previous one that we answered. In the datasets that we have used, we have utilized datasets coming from different scanner vendors. And for further details, we suggest the audience to take a look at the paper. The main differences we observed were related to voxel resolution in these images, and also the contrast changes. And regardless of the scanner type, we also saw variations because of the population group. So we did our best effort to try to take these such variations into account to be able to build robust models. And we did an external validation to see how well these models actually generalize to such particular differences. Yeah, we hope that this answers the question.
Maybe I can tack on one more that goes in that direction. Did you encounter any sampling bias, and how did you overcome it?
We haven't noticed such kind of bias. I mean, obviously, some domains, for example, prostate imaging involves scans from male patients. What we have been basically looking lately is like how these actually models perform on scans acquired from female subjects, for example. We need to make sure that these images actually the models actually produce reasonable contours, and these are the kind of like robustness aspects that we have been looking into. And regarding other type of variations, we try to cover like a resolution, contrast changing, or imaging artifacts. But there could be always like a variation that we may not have considered so far. So it's still an active area of research, and we're improving our models every day.
Thank you, Ozan.
Anton, I'm not able to see more questions related to the toolbox. If you see any, please feel free to pick and answer, please.
Okay. Do you want to pick one from what we have in the inbox now?
Yes, I think we can do that. There's a question on what was the GPU model and memory capacity you used. This is a new question. Maybe you can answer.
Yeah. We were using NVIDIA GPUs with 24 gigabytes of memory per node for the training and also for the inference. What else do we have here? There's one on federated learning here. Ozan, should we take that one?
Yes, if you could ask the question,
okay,
I can provide better answer. Yep.
Are you using federated learning? Okay, it's actually two questions in one. So, are you using federated learning and all? And the second question is, did you build your model based on the unit architecture? Second one, okay. I can safely answer, yes, it's a unit. But federated learning?
Yes, very good question. No, we are not using federated learning. It's an research area that we are closely exploring and keeping ourselves up to date. But the models are not trained using federated learning. There is one thing that to note, I think is important. When we train our models, we make sure that our data sets are clean and they complement each other. And data quality is very important for developing reliable and robust machine learning models. So this has been the particular focus. And but in the future, we might actually consider such research areas.
Okay.
Maybe we can take one last question, Anton, and
yes, and then let's wrap up.
Okay.
There's one question here. Would it, would it be able to implement attention based in the attention based on the CNN architecture? That's the question.
It's an interesting question. It's an area in which I have done research in the past. Yes, it is possible to implement attention unit within the unit. Please have a look at our GitHub repository, open source toolkit. it can be incorporated into the unit architecture. And but in our applications, we haven't considered yet.
Thanks very much, Ozan. Okay, we're at the end of our allocated time. Thank you all very much for attending today. We appreciate your participation and interest in particular. If you're interested in learning more, there are a couple of resources listed on the resource list that you should see within the webinar on the right side of your screen. So this includes lists to our team homepage and to the blog post and the paper that we presented today. And yes, this is open source. So our results are out in the open, and we will look forward to seeing how you build on top of this work and hopefully together evolve healthcare in a great new direction. Thanks very much, everyone, and have a great day.